Good afternoon, everyone. So it's my great pleasure to introduce today's speaker, Dr. Thomas Jones. Dr. Jones received his PhD from the University of Alabama in Huntsville in 2006, and his bachelor's degree and master's degree from the University of Oklahoma. And since 2010, he has been a research scientist with SIMS and CSER, right?
Yeah.
And as a part of the warning on forecast project. So where he has focused on improving the satellite data simulation and developing the tools to improve the real-time severe weather forecasting. He leading the development of the wolf smoke system in 2020, and currently he's working on the dynamic coupling of Wi-Fi behavior with the atmosphere condition to improve the Wi-Fi and the weather predictions. Beyond the research, Dr. Jones plays a critical role in real-time WAPS operations, providing the satellite-related support to forecast and developing several widely used WAPS diagnostic products. Dr. Jones also contributed to the CSER community through the committing service, organizing the 2024 file weather workshop and maintaining the students, include the master student and the PhD student, and the teaching on satellite data simulation. So please join me in welcome Dr. John. Dr. Jones, please.
Yeah. Thank you for that introduction. Can everybody hear me?
Yes.
Okay, cool. What I'm going to talk about today is just a general overview of the one-on forecast system, kind of its design and applications. The first half of the talk will be pretty much, kind of the basic one-on forecast system justification, design, and goals. And the second focus will be kind of on the fire weather applications, as both me and we have a both have proposals for the recent WPO fire weather project, and that's kind of initiated a collaboration between them and us on some fire weather and smoke emissions forecasting. So I'll kind of emphasize that toward the end. So to get going, WAFS has been in development and has been in a concept for a long time now. Convective allowing models, the concept first began back in the 80s and 90s. And in the mid-2000s, they became kind of an operational thing, at least over CONUS and regionals. The assimilation techniques have improved. In 2009 or so, the Dave Stentrud, who was the original one-on forecast director here, put out the concept of the one-on forecast system. And development of the system began in 2010. The initial goal was for rapid cycling assimilation of radar data every 15 minutes to improve forecasts of basically to increase tornado warning guidance was the baseline justification. Now, as development has proceeded, by 2015, we were able to do our first real-time testing, and we learned a lot during those early years. By 2018 or so, we've actually been able to actually do testing for at least like 1 month for hazardous weather test bed, other test bed activities later on. So we're actually to run it in a semi-operational environment for multiple days in conjunction with the Storm Prediction Center, the Weather Prediction Center, and various weather service offices. Recently, we have added the smoke and fire weather capability to the system, and as of this year, the system is being transitioned to the OSTI and their VLab system. So the 3 links that I have above, one is for our research WAF smoke output. The second one, it was our real-time forecast link up until this summer. And the red one is what is the real-time link to the system today. So that gives you a quick overview of the overall timeline of development. Oops. Sorry. Okay. So in graphics, what am I talking about? So we have a storm scale ensemble modeling system, and it provides probabilistic prediction of high impact weather on time scales that go between the weather watches. And weather watches you kind of think about are say a 6-hour concept to warnings, which are often sub-hourly. So we're kind of focusing on that 0 to 6-hour forecast period. So hypothetically, these aren't specific. This is actually an actual forecast with just idealized graphics overlaid. So we have a forecast before convective initiation. The red box is a concept of a tornado watch, and that's say 6 hours ahead of when tornadoes may happen. And then we get to the 3-hour lead time. We're starting to forecast individual storms. So in this case, you have a interesting storm in northern Oklahoma and another interesting storm in northern Texas. And looking at the 1-hour lead time, now we're actually forecasting the individual storms and the actual track and intensity of those storms. So you can see the warning is actually encompasses the forecast of the, in this case, updraft relative helicity, which is a measure of storm rotation. So you can see as the time gets shorter, our forecast gets more and more certain. And since we're a probabilistic product, you can see the probabilities in a smaller area increase as you get to higher, shorter lead times. And okay, and moving next. So here's kind of a really an example of how the system works. I'm not going to spend too much time on this chart. It's a complex system. So what we do is this is a regional domain system. So in the morning or whenever we want to start the system, we have to we select a domain center point with a overall size of 900 by 900 kilometers. So you can see the example of the kind of the green box and the white background. The blue dots indicate the 88D radars within that area that we need to collect radar data from. And then we also get GOES, our satellite data, MRMS reflectivity data, and radial velocity data, and then surface information from where it's available. The baseline system is generally initiated at 15 UTC, although we have different start times are available now. It's a 36-member ensemble, and we assimilate radar satellite conventional observations at every 15-minute at each 15-minute interval. And one of the key aspects of one-on forecast is our data processing runs is very efficient, because to do this we need very low latency. So an analysis cycle is started 7 or 8 minutes after the analysis time, and is completed within a few minutes after that. So 1515 analysis is actually done by about 1525, and the forecasts are initiated, or a forecast would be initiated at an analysis time after that. We'll generate 0 to 6-hour forecast on the hour. So after a couple of hours of cycling and spin up, at 1700, we'll start the forecasts. So at each hour, we'll start a new set of 6-hour forecasts. And depending on the mode we're running, we may also run 3-hour forecast at the top of the hour, 1730, 1830, etc. And the model usually runs out several hours, and can be ended at 3 UTC or 6 UTC the next day, depending on the overall time window. So an approximate run time of 15 to 18 hours. And once we run all the system, then we have a post-processing portion that calculates does the post-processing, calculates all the graphics. And we also have sort of a machine learning component that takes our output and does some machine learning forecasts on that as well. So there's lots of steps from the observation processing to the DA to the post-processing, and it's taken us several years to get this to work as we want it. And we still find interesting things every once in a while. One thing I want to that I like always showing when I talk about one-on forecast is it's kind of based on the HER model, and it's related from a code-based perspective, but it's not the HER or the HER smoke. The HER is designed for the sort of the 6-hour to 2-day forecast problem using deterministic forecast. WAFS is primarily focused on the 0 to 6-hour problem using probabilistic forecasts. Both of them run a dwarf-based LUC-LSM 36-member DA system, but HER is updated hourly. Ours is updated every 15 minutes. We do forecast ensemble output, which they do not. We also assimilate radial velocity data, GOES cloud data. The multiple PBL schemes is in the current system. That very well may change in the future. We may move to some stochastic perturbation stuff. Well, we use a locally developed cloud microphysics scheme. And one key component, I believe, that's helped forecasters is we generate our forecast output at 5-minute intervals, and the output, a 0 to 6-hour output, is available within 30 minutes of the analysis time or the beginning of the forecast time, and the output is done as it's plotted as it's made. So one of our goals is to have that data, that forecast, to the forecasters as fast as possible. The one limitation of that is we create thousands and thousands of images every forecast start time. So it's challenging to keep all the resources together. So it's a much more complex, it's much more resource challenging challenge than the HER currently. So just an idea of what WAFS provides. It provides accurate initial conditions for individual objects, thunderstorms, smoke plumes, whatever, and it's generated through the rapidly cycled data assimilation of the high spatial and temporal resolution radar and satellite data. We generally get a skillful short-term forecast of analyzed objects, and we'll get less skillful predictions of objects that weren't well analyzed, and or there are well-analyzed objects in an incorrectly analyzed environment. The one-on forecast guidance is probabilistic, so we have a lot of probability greater than or less than for various parameters. This gives you a range of potential outputs rather than a single deterministic forecast, and whether it's a large spread or a small spread in our forecast can give you an idea of the certainty of what may or may not happen with a specific storm. 1 second. And with the 15-minute cycling, it allows us to update the ongoing convection characteristics and in some cases the atmospheric conditions as new information comes in at every time, which is another advantage over some of the other systems. Effective use of real-time guidance is we have to be sure that the identification of objects are accurately analyzed and compare those that are not. And if for objects that aren't analyzed, should not use those. A forecaster should be careful with those. And a forecaster also needs to be careful about the accuracy of the surrounding environment, including spatial errors and air mass boundaries like dry lines and cold fronts. Has some limitations over the overall system. So if we have convection forming rapidly along a dry line or something, something can go from no storm to severe storm in 20-30 minutes. For a 15-minute cycling DA system, it takes approximately 1 hour from the beginning of where a storm is detectable from radar and/or satellite data to properly spin up that storm in the model. So CI, convective initiation, is a challenge, and the system as it's currently designed will always be a little slow with that. We do have a spurious convection problem at times in certain environments. So especially what's the right word? Especially in warm sector, unstable environments, we have excessive false alarms. We've been working on that, and we have some ideas to improve that. And if we have early spurious convective initiation associated with those false alarms, it can corrupt the larger mesoscale environment downstream, and negatively impact forecasts that way. 3-kilometer grid spacing is not, I would say, optimal for forecasting smaller storms or smaller storm characteristics. Also, sharp gradients in moisture, temperature, etc., may not be captured well. Can't resolve the interstorm processes like, what's the difference between a low-level mid-cyclone and mid-level cyclone. Also, 3 kilometers you're not going to forecast a specific tornado. So one thing I always the way I like to term this is, we're not really forecasting tornadoes, we're forecasting rotating thunderstorms, is what I like to say. And it also limits the resolution of the assimilated observations. It's not really optimal to assimilate 1 kilometer radar data onto a 3-kilometer grid. So future versions will run at higher resolution to hopefully take into account some of the finer scale information in both the radar and satellite data. And as I've mentioned, misplaced boundaries can result of storms being initialized in an unfavorable environment. Thus, the model will kill them as soon as they, or just a few minutes after they assimilated. And then one of the challenges is really we can only assimilate surface observations because of the latency requirements we have. Things like ACARS data, soundings, etc., are not available to correspond with our cycling requirements. Basically, if the observation isn't available 6 or 7 minutes after the analysis time, we're not able to use it. And so one of our challenges has been getting to work with people to make the observation processing as quick as possible. So I just got an example forecast from our website yesterday. It's from a severe weather outbreak on May 18th this year in Oklahoma and Kansas. So the left-hand plot is what we call our paintball plot. Each of the kind of colored dots is a reflectivity greater than 40 dBc from a 0 to 6 hour forecast period. So you can see each color is one member. And you can see that as time increases, the spread in the members increases. So you have kind of greater coverage of storms. The black dots are the observed MRMS reflectivity. So you can see from an overall kind of big picture scale, the 6 hour forecast. Oh, I'm sorry. I only made the loops out to 3 hours. Forgive me. The 3 hour forecast of the locations of storms is pretty good. You can see I've also plotted the severe and tornado warnings that are valid at a particular forecast time. And in several cases, the warnings, you can track the warning forecasts and the warnings and the reflectivity forecast track well with each other, especially in a few places in Kansas. On the right-hand side, same forecast time, but this is updraft helicity, 2 to 5 kilometer updraft helicity greater than 60 meters squared per second squared. And this value is based off various research that we've just done to kind of discriminate between what is likely tornadic and what is likely not tornadic at least in a Southern Plains environment. So you can see several of these high UH swaths is what we call them, have tornado warnings and tornado reports associated with them. But you'll also see that a couple of swaths, especially one in southern Kansas, do not have warnings and tornado reports with them. So while water forecast is a good guide to tell you where there's the potential of rotating thunderstorms, it doesn't necessarily tell you that every storm will or will not produce a tornado. But this is a good, I just wanted to show an example of the overall guidance and what the 5-minute output gives you as far as sort of morphology of how things evolve. Since one of the things that I did, my initial job was working on satellite DA into the system. And a few years ago, we had a case of one of our early usages of the system in real time by the SBC, where they sent out a mesoscale discussion based on a Warner forecast output. And for this Warner forecast output, which the operational version is in the center, that had both radar and GOES-R satellite data in it, you can see that the forecast UH corresponded to a very a severe hail track that was several counties wide as it moved to the southeast, with probabilities greater than 60, greater than 60, 70%, well into the 6-hour forecast period. If we only use radar data, you'll notice, which is the left-hand plot, you'll notice that the forecast is for a weaker storm, a storm that basically dies off quickly and does not track southeast. So the point I want to make here is, while the initial system was designed from a radar-based perspective, adding in satellite data and more recent and other information does improve the system, and this improvement, does impact real-time usage. So satellite's important too. Another example of operational usage, and this is occurred on March 14th, and remember this date for later. As of late this year, we've probably had near 300 examples of running one-on forecast in real time that it's been utilized by Weather Service or others. And based on this forecast, in the evening, Weather Service called in emergency managers in several counties for the potential for tornadic development. And as time went on and the forecast became more concise, the Weather Service pre-positioned resources, issued a special weather statement, and then they were issuing, sending people to shelter areas, and 2 hours after the initial one-on forecast idea was put out there, or the one-on forecast decisions were made by the Weather Service, an EF3 long track tornado was in Carter County, and this is I believe this is the northern storm. Sorry, yeah, it's the central storm in the plotted domain. And they believe the reason for the low loss of life was a special weather statement that was put out as a result, at least in part, based on one-on forecast output that was available to the Weather Service office. So that was kind of the overview of the basic system and how it's been used. Since my current emphasis is with development of fire weather forecasting in the system, I'm going to kind of transition to that for the second portion of this talk. One-on forecast was primarily developed for thunderstorm hazards, but as time has gone on, we've expanded this to fire weather, and we also have tropical cyclone applications as well. And so 5 years ago, we had the thought of expanding this for fire weather and smoke forecasting, and we've realized that there's quite a bit of potential here. So how can we use WAFs in a fire weather phase? I like to think of it as there are 3 potential applications. We have the pre-fire environment. So we ask ourselves, are the atmospheric and land surface conditions favorable for a wildfire to spread? And this is where you look at your forecast wind speed direction, level of humidity, surface fuels, elevation characteristics, etc. And then we look at our active fire phase. So now that we have an environment favorable for a wildfire, and a fire is initiated, what are the impacts associated with the smoke plumes, and what impacts do the thermodynamic characteristics of the fire itself have on the surrounding environment? So aerosol concentrations, visibility, atmospheric feedback, pyro convection, etc. Finally, one-on forecast has been designed for flash flooding for analysis. And one thing that is a concern is when you have, especially in mountainous regions out west, after a fire, you have a burn scar where the trees and grass has all been burned off. And if you have flooding rains in that area, it's much more susceptible to mudslides and things like that. Sorry. So that's another. So we can place burn scar analysis and fire and flash flooding forecasts on the same to give an idea to basically say a forecaster, okay, if we have a heavy precipitation over a burn scar, that's something we need to highlight in a forecast. So what's gone on to extend WAFs to fire weather applications. So, it's something we feel like the time has come, and given the very high visibility fires that have occurred over the last couple of years in both the central US and the western US, there's a lot of emphasis on improved forecasting of the conditions surrounding them. So, we generate the parameters related to the likelihood of wildfire ignition based on the atmospheric conditions, which one on forecast already does pretty well. We just are tuning the graphics and output products for fire weather applications. And then we added a smoke aerosol forecasting and assimilation capability based on the original HER smoke code, and it's been modified to account to work in a sort of one on forecast environment. And we're also focused on the high temporal frequency and small scale movements of these features. And that's not being made by any other model out there that we know of. And finally, and this is sort of the current project, is to apply WAF's output to fire spread models to actually forecast the movement of the fires, the evolution of the fires themselves, and the atmospheric feedback between the wildfire properties and the environment. So I mentioned that standard one on forecast has been used up to 300 times. WAF smoke, is much newer development, and we've probably run over 30 cases in both retrospective and real-time modes. I'd say the number of real-time usages is probably 8 to 10, if I'm counting correctly. Most of our domains are over the central and western US. We did run a fire over New York once. And we also will have future capabilities for Alaska and Hawaii fires. So it's not just focused on one area. We can run the system pretty much anywhere over CONUS, and in the relatively near future, hopefully have an OCONUS configuration. And so what makes WAF smoke a little different? It's basically we enabled radiation smoke feedback. So if we have a thick smoke plume, the surface measured solar radiation is less in the model to account for that. So if there's small scale cooling, will be observed in under a thick smoke plume. There's no feedback to the microphysics or anything else yet. And the smoke and fire and the initial conditions are taken from the operational HER forecast, valid when initiated at our start time. And one difference from the HER is we use fire radiative power retrievals from GOES east and west, 18 and 19 now, 15-minute intervals, so that fires which initiate or dissipate during the cycling period are analyzed and updated. The HER currently uses polar orbiting data, so the coverage and latency on that doesn't capture rapidly evolving and rapidly initiating fires nearly as well. The RFS does use GOES data, but on an hourly basis. So updating the fire at 15 minutes is one of the unique aspects of our system. And then we've added a fire weather panel to our display software that includes several new fire weather products. I should also talk about the fire radiative power briefly. So this is the parameter that goes into the model that initiates the fire and emissions that we are forecast. So it represents the amount of thermal energy that's released from the fire. It's detected from satellite imagers, primarily using the shortwave 3.9 micron channel. And this is available aboard MODIS-like, VIIRS-like, and the ABI instruments and polar orbiting and geostationary satellites. The retrieval algorithm gives you the fire radiative power, an estimate of size, temperature, intensity, retrieval quality, etc. And these parameters are translated into the amount of aerosols injected to the atmosphere using a 1D plumite model and embedded emissions model. And then the aerosol concentrations and injection heights that are done internally, that are estimated using these internal models, are sent back to the main model analysis to be forecast. and are allowed to evolve in the forecasts themselves. I have a couple of examples here. One's from a June 17th fire in New Mexico. You can see the dots indicate FRP retrievals. It's visible data. So you can see smoke plumes emanating from several detections. In this case, there's 2 primary fires. And another case, which is on February 27th, 2024 in Texas, you can see many, there's 100 or so fire FRP retrievals there. You can also see in the northern, there's a cold front moving south, which impacts the evolution of the smoke later on. One thing that's interesting, you'll note that you really don't see the smoke. The smoke plume is not as evident on this image as it is on the other image. And keep in mind the cloud impact later on, because clouds can contaminate the quality of the fire rated power retrieval. And I will show that toward the end. So a few examples of our pre-fire products. Simple, we have low-level relative humidity, and then probabilistic 90th percentile 10-meter or near-surface wind gusts. So this is gives you an idea of humidity, if that's less than 10% or so, and then we have wind gust potential upwards of 50 to, in some cases, 60 knots. That's a very conducive environment for potential, fire spread. We also have some derived products that were developed in collaboration with the Weather Service office here and some people at Texas Tech University. It's called the Red Flag Threat Index, and it incorporates 2-meter relative humidity and 6-meter wind speed and gust parameters, and into a parameter that's designed to determine whether or not the forecast environment exceeds certain thresholds for extreme fire conditions. The original product was based off climatologies of red flag fire conditions on individual ASOS sites. We modified the climatology to some extent based on the CONUS hourly reanalysis product from the GSL, which is the RTMA. And we wanted to expand the reach beyond the Southern Plains. So now it's available in much of the Western US. It's not really a viable product in the East CONUS yet, but it's something we're looking into. And so basically for relative humidity thresholds, a value of 1 to 5 is assigned to that, 5 being the driest possible conditions. And for wind speed, another 1 to 5 threshold, 5 being the strongest potential wind speed. So in the final RFTI value is just a summation of those two. And here's a plot of that for April 22nd, 2002 in New Mexico. And you can see that we go from areas that are 0 to 1 that are in Western Texas and in Colorado, up to values that are basically that are up to 9 in areas of New Mexico and southeastern Colorado. And any value greater than 5 represents an area that is considered an area that should be closely monitored. Values of 9 or 10 are considered something. This could be a very bad situation event. And for this case, there was a very large record-size fire in northern New Mexico during this day, and it evolved, and there were some other fires in Colorado as well. So this was a high impact day, and the forecast environment corresponded to that really well. So now that we have a favorable environment, what do our active fire products look like? So what we call smoke is actually total column integrated PM 2.5, which obviously doesn't account for all the aerosol characteristics in different sizes that are actually injected into the atmosphere. So it's not the best of assumptions, but it's what we have right now. And so we'll have like a total column product on the left-hand side, so that gives you the amount of aerosols in the entire column of the atmosphere. And then we get another important product is low-level aerosols. In this case, it's a 0 to 200 meter product, which that's important for air quality and what smoke will actually impact people on the ground. Tells, should people take cover? Should people stay inside? Should firefighters be careful about visibility, etc. And then, like with rotation, we have probabilities of smoke greater than certain thresholds. And in this case, the smoke plume is very well probabilities are highly concentrated. I should also mention that since we're an ensemble-based system, we can account for the uncertainties in FRP retrievals. So every assimilation cycle, when it's updated, random noise is added to the retrieval for each member so that we have some spread in the potential solutions based on fire intensity. Some other products, we have a visibility product, so it tells you, if you need to watch out for near surface visibility, air quality. And then we also have synthetic satellite imagery, so you can kind of see where the smoke plumes are. You can also see where the clouds are, and the system does a pretty good job at distinguishing between what is a smoke, what kind of looks like smoke, and what looks like clouds. So post-fire products, and I won't really go into this too much. The black lines on these plots are burn scars, which were areas where fires had previously occurred. And this was just a case where we had a monsoon case in 2003. The colors indicate precipitation greater than I think it was 1 inch per hour. And in some cases, you can see where there's paintballs overlay burn scar areas. So where you have a high threat of heavy precipitation over burn scar, that's something that people look at when they're looking at potential impacts or forecasting potential impacts. So operational usage of the fire weather aspect of the system. Remember March 14th again. It had a severe weather component and a fire weather component. And during this day, we actually ran two domains. We ran two domains, severe weather domain and a fire weather domain. And in Oklahoma that day was basically a record fire weather outbreak. And we had dozens of high impact fires. We issued the Weather Service Office here in Norman and Tulsa issued a record number of fire weather warnings. And you can see the forecast surface visibility over a 3-hour period as a function. And you can see the multiple fires, and you can see how the visibility evolves as the overall system moves east in the wind direction near the surface changes. It's a very high impact day. And WASP was able to identify new wildfires in the forecast system, and they were able to use the forecast environment to kind of indicate where, which fires might be the most dangerous after they developed. And it was noted that no other operational model they had access to could give the information like this. So another operational usage has occurred in August out in Utah, and it's kind of associated with wildfire support. So there was a grouping, I think a large concert or something along those lines, but a large grouping of people that they were concerned could be in a fire weather situation based on the conditions. And kind of the location was that black circle. And, they had very low humidity, high winds. And so the kind of put out a note saying that, there was potential for, if the wildfire would develop, there could be potential for significant development if that were to happen. Fortunately, in this case, the wildfires did not develop in this environment, and there were no major problems. But it does give the forecast the potential to know what areas would potentially have the highest impact if a fire were to form or to occur. So finally, we'll talk about some of the ongoing research activities with the fire weather component. First I want to talk about is the next generation fire system. This is a new FRP retrieval algorithm built from scratch using new detection techniques developed by NSSL and the University of Wisconsin, and has many advantages over the current sort of level 2 products from the GOES and polar orbiting data that are operationally transmitted. It's got feature tracking, improved geolocation accuracy, much better performance in cloudy regions and dusty regions, and it's more sensitive to smaller fires. And if you recall the March 14th case in Oklahoma, there was also a massive dust storm that was ongoing at the times of the fires. So you had smoke and dust with basically surface visibilities near zero over a large portion of the state. This large area of dust actually impacted the retrievals, quality of retrievals quite badly. So on the plot, the time series plot that I have in the line plot, I have at 5-minute intervals, I have the total FRP for all fires in the domain at that time. The red line is the normal GOES level 2 FRP product. The black line is the same, the NGFS version of that product. So you can see they both start off kind of similar, but as you get after about 20 UTC, and that's when the dust storm really got going, the overall intensity of the level 2 product kind of levels off. But the intensity of the NGFS product continues to increase and peaks at about 22 to 23 UTC, which was consistent with what was observed. And you can see if we swap out the NGFS, if we change the GOES level 2 data with NGFS data in the forecast, which is the center plot, the amount of smoke increases significantly. And you can see that when the third plot on the right is NGFS minus this basic level 2 smoke forecast. And you can see, with the exception of one fire, that the amount of smoke being generated when we put in the new retrievals is much higher, and it also gets smaller fires that were not retrieved well in the original product. So that's something we hope to actually integrate into sort of our operational feed within the year, because it's a very significant improvement based on what we're currently using. One of the also challenges with the system is right now we're not assimilating any information on the smoke plume itself during the cycling. So we're relying on whatever assumptions are in the emission modeling and how that smoke spreads in the atmosphere. So we're not able to correct it during the cycling. However, one of my previous projects involved looking at wildfire characteristics from radar data. And you can determine what is wildfire related or lofted debris from wildfires. Those are observable from a precipitation radar such as WSR88D, and their polarimetric observations make it possible to classify that information, the lofted debris, from just normal liquid and ice hydrometeors. And this is being increasingly used in sort of a nowcasting environment when we see wildfires on radar. I should note that the radars are not sensitive to the smoke aerosols themselves, but the larger debris that are lofted that correspond to the aerosol locations. But you can make some crude relationships between the smoke aerosol concentrations and where the debris is, and its movement. So while assimilating the radar reflectivity associated with smoke plumes is still a step too far, assimilating the velocity movement of those smoke plumes is doable, because the Ford operator in the model doesn't care what particle is actually moving. It's just assuming you're assimilating a velocity of a particle in the model wind field. So for the June 17th, 18th, 2024 fire in New Mexico, we assimilated some radial velocity data over at every 15-minute intervals using our same system. And on the lower left there, you can see that I have visible imagery, and then I have the contours of ensemble mean total column smoke greater than 2550 and 100 milligrams per meter squared, which is the blue, green, and red lines. So you can see without VR simulation, the blue and green lines do not match up with the visible imagery valid at the forecast time at all. The forecast has smoke too far north and not enough east. If we assimilate the radial velocity data, we actually improve the forecast. We actually invect more of that smoke eastward, and we reduce the northern bias in that smoke compared to the visible data. So we're actually improving the overall smoke, at least the evolution of the spatial evolution of the smoke. Whether or not we're improving the concentrations of the smoke in any individual location is something that needs further work. Some recent research I've done, which is actually coupling the fire atmospheric model with WAFS, so I call it WAFS fire. And so this is a fully coupled kind of WRF S-fire system, and it's based on the fire detection in GFS. So for a Oklahoma fire on October 29th last year, we had several fires in Oklahoma, and this is using the fully coupled system. So we have, you can see the very north to south or south to north smoke plumes and from the individual fires. And I also wanted to plot the MLK, or the most unstable cape. So if you look closely where the fire originate, you can see several kind of orange and red dots, which indicates that the thermal anomalies from the fire itself is impacting the environment and giving you areas of localized instability. And for examples where there might be enough moisture, we would be able to forecast things like pyrocumulus and eventually pyroconvection. So that's where the system is going in the future. And also, we want to use forecast output to look at the fire spread itself. Of course, this requires very high 50-meter resolution or less forecast systems, coupled with the latest surface characteristics. This is hard to actually fully couple, but if we can use that high resolution output from, say, the previous slide to initialize the fire spread models, we can update those fire spread models much more rapidly than is currently possible with existing systems. And to conclude, WAFS represents a new forecast concept for watch to warning applications that is in the process of being transitioned to an operational environment. A decade of development has gone into this, and it's already an important tool to be used by the Weather Service, as a Storm Prediction Center, Weather Prediction Center, and others. Had a lot of lessons learned in developing this. Basic, as you can see, the basic system can be expanded to many applications, and fire weather forecasting is a current emphasis. And we don't know what the future may bring, but we will see. And thank you.